Welcome AP Stats to yet another exciting day of distance learning. Today we're going to cover lesson 3.1 and the topic is scatterplots. This is something I'm assuming you're all pretty familiar with, plotting XY points. You've been doing that hopefully for quite a few years, so I'm not going to spend time going over how to plot an ordered pair point. I'm going to spend more time talking about how to label your axes, how to determine what variable goes on which axis, and most importantly, how do I read the scatter plot once it has been created. So, up until now, we've been doing one variable data, or univariate data. A scatter plot compares two variables, and exactly two variables. We don't have three-dimensional scatter plots. And again, if we have univariate data, we're not making a scatter plot because we only have one axis with a variable. So a scatter plot is going to compare two quantitative variables, right? If we have categorical variables like your favorite color, you don't really have an axis that works for favorite color and making a scatter plot, because it's kind of arbitrary. If I say red then blue or blue then red, right? The order is arbitrary with categorical data. So when I have two quantitative variables, that is the appropriate time to make a scatter plot. Okay, so my two variables, one of them is what we call the explanatory variable. And it's called that because it's trying to explain the outcomes of the other variable. The explanatory variable will always appear on the x-axis. Okay, so that's important to note. It's also referred to, maybe you've heard this term in the past, it's the independent variable. So I'm guessing you've probably heard independent variable, but explanatory variable is a new vocabulary term for you. But they're the same thing. All right, now my y variable is called the response variable. Okay, it goes on the vertical axis, and it is referred to as the dependent variable because in theory, its change is depending on the independent variable's change. So a very common thing would be to see time as your independent variable. So really a time plot is actually a way to compare two variables, but it's not a scatter plot because you're connecting the points, right? But a time plot, time is always your independent because you're saying, oh, time is having an impact on, say, my stock price or whatever else that you are interested in. Okay, so those are your two variables, explanatory on the x, response on the y. Now, what's difficult for some students is if you're just handed data, how do you determine which variable is explanatory and which is response? Well, you can think in terms of independent and dependent. Maybe you've thought about that in previous math classes. It's the same type of thinking. But one question to ask yourself is, are one of the two variables affecting the other, right? The explanatory variable affects the response variable. And another thing to realize is that time is pretty much always independent. So if time is one of your two variables, it's going to go on the x-axis. But there are examples where you have two variables that you just can't figure out which one should be explanatory and which should be response. And when that happens, maybe you could graph it both ways, or you can just come up with a reasonable argument why you graphed it the way you did. All right. Once you have your scatter plot, these are the things we want to look for when we're reading it. Okay, first, what's the form of the scatter plot? In other words, when I look at the relationship of the two variables, do I see a linear relationship? Do I see an exponential relationship? Do I see a logarithmic relationship? Do I see a quadratic relationship? So on and so forth. So that's called the form of the graph. Also, look for any clusters of data. Okay, clustering of data can sometimes be explained by a categorical variable. And other times there's other explanations, but look for clusters of data. Okay, after form, you want to look at the direction of the relationship. Okay. There's basically two choices here. You can say there's a positive association, right? That means as the x variable increases, the y variable also increases. Okay. It can be increasing in a linear method or in a curved manner. It doesn't matter, it's just you're seeing increase together. Okay. Then you could, on the other hand, have a negative association between your variables. Okay, so in other words, think negative slope. As your x variable increases, your y variable decreases. Again, it could be linear, it could be a curved relationship. I guess there is a third relationship, and that is no relationship at all, right? A constant relationship. So as your x or explanatory variable changes, your y variable doesn't respond, right? So that would be a third. All right, moving on. The strength of the relationship. So the strength is how well does your scatter plot fit whatever form you've chosen. So how linear are your points? How exponential are your points, right? Are they really close, or is there quite a bit of variance, or in other words, scatter, right? Hence the name Scatterplot. For the rest of chapter 3, we're going to focus on linear. So right now, I kind of just put linear in the notes because that's what we're going to be focusing on. In chapter 4, that's when we're going to start looking at some of the curved relationships. Okay, but for now, it's when I say strength, it's going to be how well does it fit a line. Okay, next, outliers. Just like with univariant data, when I have, we call this bivariant data. When I have bivariant data, we can have outliers. Now with univariant data, we have a formal calculation to identify if a point is an outlier or not. When I have bivariant data, we're not going to give you a formal calculation for that. So you're simply going to notice a point that is extremely different from the other points in a vertical direction. Okay, an outlier is extremely different in a vertical direction. So let me show you real quick. So let's say I have a scatter plot. Okay, it looks like this. So I have a clear positive association with my points. I have a linear form. Okay, so right now there's no outliers. If I added a point down here, that would be an outlier because it's extremely different in the vertical direction from the rest of the points. Okay, so that is an outlier when we talk about bivariant data. Okay, it has a large vertical distance from the other points. Now, let me show you another type of point that is something we should note on a scatter plot. Let's say we have a cluster of data, right? Cluster of data. And right now it looks like we have a strong positive linear association, right? But then I add a point over here. Okay, this point is not called an outlier. This point is called an influential point. Okay, and we'll talk more about this in the next lesson, why that's influential and why the other point is an outlier. But for now, just realize points that have a large vertical distance from the others, those are called outliers. Points that are all off by themselves horizontally, those are influential because they're going to have a huge influence on our regression line. You've probably tried to do lines of best fit in a previous math class. So the idea here is, on my first example, my line of best fit is still going to be kind of going through all of these points despite the outlier, right? My line of best fit's not all of a sudden going to come over here because of that one point, right? Because it would move it really far from lots of points. So my line of best fit would still be somewhat unchanged, right? The outlier does change it, and it does, weaken the association. Versus over here, the influential point, right? Without it, I have a graph that's got a strong positive linear association. But once I throw that influential point in, it will change my entire line. It'll pull the line over to itself, because going like this with that influential point puts me closest, minimizes the gosh, I'm getting into lesson 3.2 quite a bit here, but it minimizes the residuals, the vertical distances between the points in the line. So an influential point pulls the line to itself. It changes the line greatly, and that's because it's extreme in the x or horizontal direction from all the other points. Okay? So anyway, we'll get into this more next lesson. All right. The other thing, I kind of mentioned this earlier. If you suspect that clustering is occurring, or there's some kind of pattern occurring that's due to categorical variables, then use different symbols, right? So if you have, say, let's just make another example real quick. Let's say I have a plot. Okay, and I see these two clusters of data. It's potentially incorrect to just connect them with a line, potentially, because I don't know what's causing the clustering. So I want to go back and try to figure out, well, is there something that this group has in common that this group doesn't, and vice versa? Does this group have something in common that group doesn't, right? So is there a categorical variable causing these two clusters? And the way to do it is, if I suspect that categorical variable is, say, education level, right? I would graph all of my data that represents, I don't know, people with a higher degree with one shape or one color point, and then all the other data with another shape or a different colored point. And then if all of a sudden, hey, these are all red and these are all blue, then I can go, that's explaining why I have the two different clusters of data. And it might be wise at that point to break it apart and have two separate graphs, okay? So that's how I handle categorical variables. If I suspect that something's going on, I go back, I regraph, and I graph the points with a different color or a different shape or symbol. That way I can confirm, or hopefully confirm, but possibly eliminate that as a suspicion. Okay. So, moving on. Here is a question from an AP test that's been released. So go ahead, pause the video here and read the question. All right, so after you've read the question, some important things to note. We have 20 different strengths or doses being given of 2 different drugs. Each dose is given to 40, there are 40 different groups, and each dose is given to more than one person. That's what's important. We're giving this drug to more than just a single individual. So the points that we're looking at on our graph are the average responses of a group of people. That's the key thing. The actual number of people in each group, that's not what we should focus on. Focus on the fact that it's the average response of a group of patients. Okay? And last thing to notice, 0 means the pain has not gone away at all. 100 means pain has been totally relieved. So let's look at the graph. Okay, so we've got drug A and drug B. And again, each one of the points in this graph represents the average response of a group of subjects. So looking at this first point up here, it looks like the average response for this group is somewhere around a pain relief of 65. But realize that's the average. So there's going to be some patients that were below 65 in their pain relief, some patients that were above 65 in the pain relief, and all those scores have been averaged together to give me this 1 point. Okay? All right, now we have some questions. So I'll look at the question and then I'll put the graph back up. First question. Look at the scatter plot and let's describe drug A. All right. And by the way, notice this is an example of using different letters or symbols for categorical variables, right? I have two different drugs on here. If I had just thrown all the points out there without the different symbols, you wouldn't see the relationship. All right, so again, pause the video, think about drug A, read that part of the graph. What are you seeing? Okay, so looking at drug A, what's the form? Appears to be linear, right? So I'm going to say the form there is linear. Do I see any clusters? Really not possible, right? Because each point is the average of the group. So because of the way the data was handled, it's not really possible to have any clustering on this graph. What's the direction? Okay. It appears to me as the explanatory variable or dose changes, I'm seeing a fairly constant relationship. It appears that dose is not really impacting the pain relief. Okay. Another way to say that is there is constant pain relief from drug A across all the different dosages. Okay, what's the strength? It's fairly strong, but this is something you should notice. The lower part of the graph has more variation than the upper part of the graph. That's important to notice. If you didn't notice that, you would lose points on the AP exam. We have more variation on lower doses. And again, something to keep in mind, each one of these points is the average pain relief of a group of subjects. So if I see this much variation when I'm averaging a group of subjects, then imagine how much variation would have occurred across individual readings, right? So individually, there must have been quite a bit more variation. And then when I averaged those scores together, I was still seeing quite a bit of variation, but averaging always cuts down variation, visible variation. So the individual scores must have been quite variable over here, and then much less so over here. Okay, but that does bring me to the next thing to notice, this point right here. If that point occurred at the beginning of the graph, it would kind of fit the pattern of there's some variation. But that point is occurring over here on the right side of the plot where things are pretty darn consistent until all of a sudden that point pops up. So this point right here, that's a potential outlier. And again, it's because of where it is vertically from the other points. And at this section of the graph, that's quite a big vertical change in comparison to the other points. So that's something to note. Okay, so that's question A. I see a fairly constant pain relief, quite a bit of variation at the lower dose, less variation, say from about 270 on milligrams with one potential outlier over here. All right, question B. Let's do the same thing for drug B. So again, if you need to, pause the video and look at drug B and think about your response. All right, so looking at drug B, you'll notice, okay, a lot of students, they want to just kind of put this together and think, okay, right, it's one line, but it's not. And this happens quite often, especially with drugs. Down here, B is completely ineffective, right? At the lower dose, it's not relieving any pain at all, right? But then at some point, the dose becomes high enough that it actually starts relieving pain. So you have to read this like a piecewise graph. We have two linear pieces, okay? So completely ineffective until whatever that is, it's 270 or so. And then from that point on, I see a pretty strong positive linear association, okay? Not much variation from the line. And unlike drug A, right, after 270, as my dose increases, my pain relief increases, right? The positive association that I mentioned, but you should put the positive association in context of the problem. So above a dose of 270 milligrams, drug B, right, is providing an increase in pain relief as the dose increases. Okay. And it's got a pretty strong linear association. No outliers. All right, and that gets us to our last question. So question C, which drug would you give? So let's pretend you're the doctor. You want to get your subject a pain relief of at least 50. So you want to at least cut your subject's pain in half. So what drug would you give, and what is the lowest strength, right? Because you don't want to over-medicate your patient. So again, take a moment, think about that, pause the video. Okay, on the surface, this looks like a very simple question. And a lot of students on the AP exam kind of miss the big picture. Okay, this is a much more complicated question than it might appear. A lot of students simply say, oh, 50 is right here. I want the lowest amount of dose. The lowest dose would be drug A, because you could see drug A at its very first dose has a point of pain relief 65. So there you go. I'm going to go drug A. I'm going to go 200 or 210, whatever that lowest number was. Done. Okay, well, if that's all you say, you're not going to get a very good score on that. Because, as I mentioned earlier, drug A has a lot of variation at those lower doses. So, yes, the average patient received pain relief of roughly 65, which is over 50. However, if you want to guarantee that your patient gets at least half their pain relieved, this is no guarantee. There's going to certainly be some patients that are scoring below 50 and some that are scoring quite a bit higher at these doses of A. Okay. That doesn't mean you can't say give drug A at 210, but you must mention there is a chance that it's not going to reach the desired pain relief for your patient. You need to mention that based on the plot. So some students will say, okay, I'll give drug A at 270 or 280 milligrams because now the pain relief is much more consistent with drug A. But again, notice even over here at 340 or so, whatever that is, there's still kind of this bounce where it looks like we may not be able to guarantee the pain relief of at least 50, right? Drug A is probably throughout its entire graph, there's probably some patients that just aren't going to quite make it to a pain relief of 50. Doesn't mean you can't give them drug A, but it does mean that you need to note that in your response. Okay, so drug A here, I might get the pain relief of 50. I'll give it a shot because my goal is the lowest dose, but there's a chance I might not get that patient the pain relief they desire, in which case, right, I need a backup plan. Backup plan might be I give them a little bit more of drug A. Now I'm here where it's less variable. But even then, I can't guarantee, right, because this is the average of lots of data, I can't guarantee that the patient gets the pain relief that's desired. So I, again, would need a backup plan. Now, somebody might have said, I'm going to give drug B. Okay, so if you give drug B, you might suggest somewhere around here, right? 320, 330, whatever this is. And your backup plan, right? If your patient comes in a little bit too low, the backup plan is give them a little more, right? Because you can see drug B has a positive association. So all I have to do to increase pain relief is give them a little bit more until they have met the desired level of pain relief. Okay, so that's really what they were looking for on question C. It wasn't like a drug A, 210, period, done, right? And that's the thing about the AP exam. These questions, they're more of a discussion. They want you to show the different options. And in this case, no one option is actually the correct answer. They're wanting you to show your understanding of how to read the graph and that no one option is necessarily the absolute best option. Okay, so that's what we were looking for there, was more of a discussion of the choices. Low dose of drug A, running a higher risk of not getting the pain relief of 50, more of a medium to higher dose of drug A, higher chance of getting the drug pain relief of 50, but not a guarantee. Or option 3, go to drug B and start somewhere around here and just increase a little bit as you need, and then you can pretty much guarantee the pain relief that you want. So it comes down to, do you want to guarantee that pain relief, or is it okay if they come in a little bit under? All right, that is the end of the lesson. Have a good one.